The point cloud multipoint control unit represents the evolution of the multipoint control unit concept that was traditionally used in 2D video conferencing systems, but for the holoconferencing systems. This presentation is going to introduce the reason why we have thought about creating such a component. Then we are going to specify what is the point cloud MCU, and we're going to explain its functionalities. We're going to give an overview of the past results that we had and we presented in this paper, and then we're going to end with the conclusions and the future work that we plan to do. Let's start with the introduction. The future of video conferencing, it's quite obvious. We all know that they're all going to become immersive experience, and mostly because video technologies are evolving. So everything that now is represented in 2D in traditional video conferencing systems will all be brought to a third dimension, to a more immersive experience, thanks to the introduction of holograms, volumetric video, and thanks to the introduction in the market of devices able to capture the geometry of the scene. So, for example, the iPhone X or RealSense, Kinect cameras. In addition to that, the content is evolving in addition to that, the content is evolving toward different direction. We have a very high quality volumetric video that of course needs some post-processing, but we also have very good quality real-time capture. Some capturing systems still need a high amount of cameras, a specific setup, and also specific infrastructures. But the technology is also moving forward some portability. iPhone X, for example, as I mentioned before, is one of the first mobile devices able to capture the geometry of the scene. Of course, the quality is not the same as for the two previous examples, but still that shows us that soon there will be the possibility of having such a technology with portability. The point cloud multipoint control unit, or point cloud MCU, is a component for multi-user conferencing systems where remote participants are represented as point clouds. As I said at the beginning of this presentation, one of the goals of the point cloud MCU is to redefine the idea of multi-point control unit. The traditional MCU that was used for video conferencing is now adapted to volumetric video and holoconferencing, with the goal also to reduce the end-user client computational resources and bandwidth usage. So the main goal is to optimize and tailor a specific volumetric video content for each user client for every participant. So this is a high-level overview of how the point cloud MCU works and where it's going to be placed. We are in a scenario where each user client has a capturing and transmission system. The capturing system, of course, needs to be at least one RGBD camera. Obviously, there are setups with more camera and more accuracy. And also a receiving and rendering module, and where the rendering is provided to a VR AR device, an HMD, augmented reality glasses, or anything that is able to reproduce the volumetric video. The point cloud MCU itself has three main modules: a reception module, which is in charge of receiving the captured volumetric video for each user; a point cloud MCU core, which performs a set of specific functionalities that we're going to explain in this presentation; and a transmission module that is going to tailor the flow for each end user. And in the next slides, we are going to start going more in detail over all these functionalities. So initially, we're going to talk about the reception and transmission module. So the point cloud MCU is capable to receive multiple streams from multiple end user clients, and of course is also able to transmit a tailored and optimized fused volumetric user stream for each end user. And connected to the reception and the transmission, of course, we have the decoding module and encoding modules. The point cloud MCU is able to perform multiple volumetric video decoding and encoding. Of course, the first stage is represented by the decoders because they have to uncompress the received volumetric videos for each user in order to provide an uncompressed volumetric video representation to the point cloud MCU core. And there are multiple encoding modules, so one for each end user that is going to be in charge to compress the specific stream for every user. In the next slides, we're going to explain the functionalities that are included in the point cloud MCU core. First of all, the level of detail adjustment. So on the left, you have an image without the point cloud MCU. So imagine that you are receiving two point clouds from two remote users at a specific resolution. This is the resolution that the capturing system is able to provide, and it's transmitted to the internet. You're receiving both at that resolution independent from the relative distances between volumetric videos. So in a situation like this, the end user client would receive a total amount of about 140,000 points. With the point cloud MCU performing a level of detail adjustment, we are able to downgrade the resolution of those volumetric videos, in this case point clouds, of those volumetric videos that are placed far away. So, for example, in this case, we are able to receive everything with an overall amount of points of about 80,000. Obviously, this is possible without changing the quality of experience for the end user because this point cloud is placed at a relatively far distance. If we observe the two point cloud at the same distance at the two different resolutions, we see that there is a visible downgrade, which in this situation is not visible. The other functionality is the removal of non-visible volumetric video. So we know that in an holoconferencing system without any optimization module, we would receive every volumetric component, even if they are outside from our viewport. If even if we are not going to be able to visualize them. The point cloud MCU receives the viewport information from every end user and knows what area of the 360 degrees world the user is looking at. So it's capable of removing what is outside of this field of view. This is an example, a very clear example of how the not needed data is removed because it's outside from the end user viewport. And finally, the point cloud MCU performs also a fusion of volumetric videos. So what happens is that everything that is assigned to be transmitted to an end user is always fused in only one point cloud. So for example, if you consider this case, we see that here we would receive two different point clouds with about 70k points each, and thanks to the point cloud MCU, we're going to be able to receive only one point cloud, so the end user client is going to need to instantiate only one decoder and receive in total about 80,000 points. The results that we have obtained have been calculated considering this experimental setup. So we have run 10 simulated holoconferencing sessions. In every holoconferencing session, we have simulated that one user is receiving two remote point clouds that in this case are represented by red and black and long dress from the A-type voxelized full body database. In order to make sure that we are able to evaluate all the functionalities that we have explained before, we have prepared a set of simulated actions that are shown in these videos. So we start the session with the third user receiving the other two point clouds at their maximum resolution. So in this moment, we are able to see both, and then the viewport starts panning toward the one, removing the other one. So we test the removal of the non-visible area. Same thing, but with the other point cloud. Then we're going to go back to the initial position, and then we start moving away from the two point clouds in order to test the level of detail selection. The viewport is moving away at different stages to see different level of details reductions. This first part of the video that you're seeing is the one without the point cloud MCU. And now you can see the same simulation with the point cloud MCU. So you will see a visible delay in the representation that will be discussed later, and also some roughness in the way the non-visible area removal and the level of detail selection is applied. This is a video of one of the first tests that we have provided, and in the future work section of this presentation, we are going to discuss how we plan to attack these specific situations. So moving to the analysis of the CPU usage, we have sampled the usage of the CPU 26 times along this whole session that was shown in the video, and we have highlighted the part of the session where each point cloud MCU functionality was active. We can see that the fusion module, indicated with the green arrow, is always active. And here, in this box, we have highlighted the contribution in terms of CPU usage reduction when only the fusion module is applied. So we can see that already, just fusing the two-point cloud, we are saving around 40% of the CPU usage. This optimization is further improved when the removal of the non-visible area is applied. So the orange arrow indicates the length of the removal of non-visible area application by the point cloud MCU, and you can see that the CPU usage is around the half of what was previously reached. Then, finally, the level of detail selection after a peak that is reached because the simulation have moved to the initial position where both point clouds are received at the maximum resolution. Then the level of detail selection increases even more the optimization that was performed by the point cloud MCU before. In addition to the CPU usage, we have also analyzed a set of other parameters. So this is the average of the CPU usage calculated along the 10 sessions and the 26 samples that we have shown before. So in average, we have nearly 70% of reduction for the CPU. We have also a slight reduction of the GPU, which is mostly given by the level of detail reduction. And then we have also considerable amounts of RAM savings and especially bandwidth. Bandwidth is the most optimized parameter. As I said before, we see that there is some roughness in the movements of the point cloud when we have the point cloud MCU. That's why we have a delay applied by these functions. This is a sequential implementation right now. So every delay is accumulated. That means that if we have an average latency of 90 milliseconds, this becomes accumulated frame by frame. So after 10 seconds, we may have 1 second of delay. And we have evaluated that when both point clouds are the lowest resolution, the average is of 89 milliseconds. When they are maximum resolution, the average is 160 milliseconds. So in the future work, one of the things that we are going to address is exactly this issue. So we're going to perform parallelization of operation and GPU optimization. Right now, we have a sequential implementation. This means that there is a certain delay, there is a certain limitation in terms of number of users that we can handle, and the delays that we have are always accumulated. Thanks to the parallelization, we're going to have just an initial delay given by the first frame reception, and then everything else is done in parallel. So we're going to be able to transmit a more constant frame rate. And at the same time, you're going to be able to increase the number of encoding and decoding instances that the point cloud MCU is able to handle. Also, the other issue that we have seen is a certain roughness in the way the functionalities are applied. So there is a delay, for example, in terms of when the point cloud shows up when the viewport is pointing at it. There was just a thresholding system implemented to decide when and how reduce the level of detail of the point cloud. So we want to refine these strategies, introducing some more intelligent mechanism that consider the distance, the navigation patterns, the number of volumetric media elements, something probably viewport aware that is able to predict before the viewport is going to point at a point cloud that this may be needed to be showed. So these are all the things that we plan to introduce in the next versions of the point cloud MCU. In addition to that, we also want to study scalability and quality of experience related to a holoconferencing experience when the point cloud MCU is introduced, exactly to validate the strategies that we're going to implement in the next versions. And this was the end of the presentation. So thank you very much. And if you have any questions, please